So good evening, all of you. So once again, welcome to Physics by Physics. And in this PGT practice series, we are going to take next chapter, that is current and electricity. So I will just give you the summary and then we will focus on the practice session. Clear? So let's see what are the important points that we have to focus on this particular chapter. So you know about the current. Current through a wire is what is the charge per unit time that is passing through a particular area. Charge per unit time crossing through a particular area, that will be a current. And if you want to set up a current, you have to supply some battery. So a battery has an internal resistance R and its EMF is E. E is called the EMF because if you connect this in some external resistance R, a current I will flow. So how current will set up? When a charge move, let's say you are moving a positive charge from negative potential to positive terminal. I'm assuming some positive charge is moving in this circuit. So what is the work done? What is the work done per unit charge? What is the work done per unit charge is defined as EMF. So EMF is the potential difference that develops across this open circuit resistance. So when you remove the resistance R, let's see, when you have removed the resistance R, this potential difference is called as EMF. This is the R is the internal resistance. This is the internal resistance of the battery. So in second point, we have summarized it. The work done per unit charge by the source in taking the charge from lower to higher potential energy, that is from one of the terminal to other, is called the EMF of the source. And when you connect this, there will be a terminal voltage. So terminal voltage is V, and this V is given by simply I into R. This voltage is V. And this will be given by simply E minus I into R, because there will be some drop across this. So current I is given by E by R plus R. And in this internal resistance of the battery is very small. So that is point number 2. You know, in Ohm's law, the electric current flowing through a substance is proportional to the voltage. Point number 3, Ohm's law. Ohm's law is what? V is proportional to I. Or this is given as V is equal to IR. R is the resistance of that particular substance. And you know that resistance unit is ohm. If you have a conductor of length L, point number 4, if you have a conductor of length L and this cross-sectional area A and its resistance is R, then its resistivity, rho is called the resistivity. Resistivity rho is given by RL by A. L is the length of the conductor, R is cross-sectional area, A is cross-sectional area, and R will be the resistance of the material, and rho is called the resistivity. And resistivity is the property of the material that depends on temperature and pressure. Is it clear? Now, if you see, electrical resistivity of a substance varies with temperature. So resistivity varies with temperature. Metals have low resistivity of the order of 10 to power minus 8, and unit of resistivity is what? Ohm meter. Resistance is ohm, resistivity is ohm meter. Conductivity is 1 by resistivity. Conductivity is 1 by resistivity. So rho is resistivity, its unit is ohm meter. And conductivity sigma is 1 by rho. And this unit is ohm meter inverse. So metals have very low resistivity of the order of 10 to power minus 8 ohm meter to 10 to power minus 6 ohm meter. Insulator have very high resistivity, 10 to power 22 to 10 to power 24 times greater than the resistivity of metals. And we have semiconductor material also, whose resistivity lies between conductors and insulator. Clear? Now, mostly the carriers of the current is what? You have electrons, or in some you have ionic crystals. There may be ions also. So mainly current is because of positive charge, movement of positive charges or negative charges. And you know that current is per unit time. What is the current per unit time that is crossing through a particular cross-sectional area? Then we have to see current density. So what is the current density? Current density is current per unit area. So when there is an external field that is applied, when there is a potential difference, then current density J is given by, this is I by A, and this value is NEVD. VD is the drift velocity. VD is the drift velocity. N is the number density of the charge, electron concentration. This is the number density. This is number density. Number of electrons per unit volume. And electronic charge, I am taking E to be the electronic charge, and VD is the drift velocity. And this current density is, J is normal to the cross-sectional area. So if current is, let's say, this, in this material, charges are flowing like this. So there will be current density J. So this will be perpendicular to this cross-sectional area. This area A is perpendicular to current flow. So this is current per unit area perpendicular to the current flow. And this will be given by NEVD, where VD is the drift velocity. Clear? So what will be total current I? I is given by NEAVD. You have to remember, take scalar quantity because I is a scalar. So this is I is NEAVD. Now, this VD is also given as mu E into E. Mu E is mobility. Mobility. So mobility is drift velocity per unit applied field. Drift velocity per unit applied field is mobility. And now see, what is potential difference? V is given as I into R. I is given by NEAVD. R is given by rho L by A. So this A will cancel out. So what will be V by L? This is rho times NEVD. And V by L is what? Electric field across the conductor. This is the, if you have this particular potential difference is V across the length L. So E is given by what? V by L. So this is E by electric field is rho NEVD. Now I am taking this as E and let's multiply it by electronic charge divided by mass of the electron. So this will give you the acceleration of the charge particle in this material. So this is, you are multiplying with E, so rho NE square by M into VD. So just see, this applied electric field is proportional to the drift velocity. If there is no applied field, net current will be zero because electrons are in random thermal motion. Although their speed is very high, but their average will be zero. But when you apply electric field, this overall electrons will drift in a particular direction with very small speed. And that depends on the electric field. So this will be the acceleration of the electron. And acceleration of the electron is given by this relation. Now, if you know that when electrons will have a random motion, they will collide with the lattice. And there will be, if we assume that electrons suffer collision with the ions in the metal, which deflect them randomly, and if such collisions occurs on an average at a time interval tau, tau is the average time collision. Let's say tau is average time between successive collision. So in that case, VD is given by A into tau. So, and A is, this is given by E into E by or let's see. This is given by E into E by M into tau. So if you substitute this value, VD is given by, this is E into E by M rho NE square by M, and VD is E into E by M into tau. So this will cancel out. And then rho will be given by, rho is given by M times M by NE square tau. This will be the resistivity. Resistivity rho is, resistivity of the material is M is NE square tau. M is the mass of electron, M is the mass of the electron, N is the electron carrier concentration per unit volume, E is electronic charge, T is the average time taken between successive collision. So sigma is 1 by rho. This is NE square tau by M. This will be the conductivity. Conductivity sigma is Ne square tau by m. Now, how does resistivity of the material depends on temperature? Just see if you have metals. Consider a case of metal. So this resistivity depends on n and tau. So as temperature increases, what will happen? N will increase and tau will decrease. Tau is average time between successive collision, that will decrease. But in case of metal, N is very high, very large. N is very large. So this is insignificant. This change is insignificant. So that's why main dependence is tau, and this will give you resistivity. Tau will decrease, so resistivity rho will increase. So in a metal, resistance of the metal will increase with increase in temperature. But if you are talking about semiconductor material, rho will increase, then conductivity will decrease. In a semiconductor also, if you see, T will increase, N will increase, tau will decrease. And in this will be insignificant. This will be insignificant. So what will happen as T increases, this will give you resistivity rho will decrease or conductivity will increase. So in a semiconductor and metal, temperature behavior will be different. So must remember this point. This is very important. Many times question has been asked on resistivity, resistance or temperature, conductivity dependence on temperature in case of insulator, in case of conductors or semiconductors. Is it clear? So note down. Now we will see in the temperature range in which resistivity increases linearly with temperature. The temperature coefficient of resistivity alpha is defined as the fractional increase in the resistance per unit increase in temperature. So how temperature changes? Let's say there are R2, R1, 1 plus alpha, T2 minus T1. So if resistance at temperature T1 is R1, this is resistance at temperature T1, this is resistance at temperature T2. So alpha is the temperature coefficient of resistivity. Alpha is temperature coefficient of resistivity. So alpha is given by R2 minus, it is defined as the fractional increase in resistivity per unit increase in temperature. T2 minus T1. This is the fractional increase in resistivity per unit increase in temperature. So this relation you have to also remember, where alpha is the temperature coefficient of resistivity. So as temperature increases, resistivity will increase. So alpha will be positive. So in Ohm's law, V is proportional to I, but there are other situations where V does not depend on I. You will see in case of diode. So Ohm's law is for linear relation. There will be non-linear relation also. Now, as I have already told you that when a source is applied, when a source of EMF is connected to an external R, the voltage V external across R is given by, so this is R, this is R, this is the EMF. EMF is the, when terminals are open, what will be the voltage? So this current is I. So V external is given by I into R, and that is given by E by R plus R into R, where small r is the internal resistance of the battery. You know, if you have to see series and parallel combination, in series resistances will add up, in parallel equivalent resistance is given by 1 by R1 plus 1 by R2 plus 1 by Rn. So you know these points. You know about Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law is at any node, algebraic sum of current must be 0, or sum of incoming current is equal to sum of outgoing current. And KVL is, in any closed loop, algebraic sum of voltages must be 0. Algebraic sum means you have to consider the sign convention also. So you know about Kirchhoff's rule. Question may be asked on Kirchhoff's rule or equivalent resistance. So these are the different points from which question may be asked in PGT exam. Now, one is Wheatstone bridge. What is a Wheatstone bridge? Let's consider Wheatstone bridge. So in a Wheatstone bridge, let's talk about Wheatstone bridge. And we will see balanced condition. We have the balanced condition. So in balanced condition, no current will flow through the galvanometer. So what will be the balanced condition? Let's see. So this terminal is A, this is B, this is C, and this is D. Let's see, we have a battery having EMF. I'm taking internal resistance to be 0, and this resistance is R2, this is R1, this is R3, and this is R4. R4 is unknown, R3 is the standard R. So we have to find the unknown resistance. So we have to vary the standard R so that this galvanometer current is 0. We have to see this condition when Ig is 0. Let's vary the resistance so that Ig is 0. So when Ig is 0, Ig is 0, potential of B is equal to potential at D. These two terminals, they are at the same potential. So what will happen? If this current is, let's see, if this current is I1, this current is I2, because no current will flow here. So this current will be also I2 and this current will be I1. In this way, current will flow. This is the back. So VAD, potential difference will be I1 into R1. Similarly, this is one such relation. And then what is VBC and what is VDC? So that is given as I2 into R4 and that is I1 into R3. Because B and D, they are at the same potential. So they will be equal. So if you divide these two, what you will get? This will give you R2 by R4 is equal to R1 by R3, or R4 is given by R2 into R3 by R1. So in this way, you can find the unknown resistor R4. And in this situation, what will be equivalent across AC? R equivalent across AC. So because R2 and R4, they are in series, same current is flowing. So this will be R2 plus R4 parallel combination of R1 and R3. This will be the equivalent resistance. So you must know about Wheatstone bridge. What will be the condition, balance bridge condition, and in balance case, what should be the equivalent resistance? So that is the summary for this particular chapter. Now we have to see questions. Let's see the questions. Try to solve these questions. Mainly focus on the practice of these questions. Practice of these questions. Let's solve question number 1. Solve question number 1. So question number 1 is, estimate the average drift speed of conduction electron in a copper wire. Cross-sectional area is given. So just see question number 1, A part. So cross-sectional area A is 1 into 10 to power minus 7 meter square. Current I is given as 1.5 ampere. And assume that each copper atom contributes roughly one conduction electron, and density of copper is given. Density of copper. This is 9 into 10 to power 3 kg per meter cube. And its atomic mass is 63.5. So you know that for a copper, 1 mole is 63.5 gram, and this will give you 6 into 10 to power 23 atoms. 6 into 10 to power 3 atoms. So what will be the mass of atoms numbered per unit mass? What is the number per unit mass? Number of atoms per unit mass. Per unit mass. This will be given by 6 into 10 to power 23, 63.5, 10 to power minus 3. This will be per kg. Per kg. So number density n is given by, you have to multiply this with the density. Number of atoms per unit mass with density will give you the number density. So this is 6 into 10 to power 23, 63.5, 10 to power minus 3 per kg, and you are multiplying this with 9 into 10 to power 23 kg per meter cube. So this will give you the number density, n will be given by, if you multiply this, I think this will be 8.5. If you calculate this value, 8.5, 10 to power 28 per meter cube. This is the number density, number of electrons per unit volume. So you have to find the drift speed. So I is equal to NEAVD. So VD is given by I by NE into A. E is the electronic charge. So I is 1.5 ampere. N is 8.5, 10 to power 28. Electronic charge is 1.6, 10 to power minus 19. And cross-sectional area is 1 into 10 to power minus 7. And if you calculate this value, this is approximately 1.1, 10 to power minus 3 meter per second. Or this will be 1.1 millimeter per second. So just see, this drift speed is very small. Drift speed is very small. And if you compare this drift speed with the thermal speed of the copper atoms at ordinary temperature. So thermal speed is given by, if you calculate the thermal speed, this is approximately under root, let's say 3 kBT by m. And if you calculate this value is of the order of 2 into 10 to power 2 at room temperature at T is equal to 300 Kelvin, this value is very high. So this will be of the order of 200 meter per second. 200 meter per second. But if you see the drift speed, that will be very small. Drift speed is very small. Although their random thermal speed will be very high. And if you see the speed of propagation of the electric field along the conductor, that will be of the order of speed of light in that material. And that is very high. Clear? So that will be question number 1 based on the drift current. Now see question number, let's see question number 3. Try to solve question number 3. Let's solve question number 3. So if you see question number 3, an electric toaster uses nichrome for its heating element. When a negligible small current passes through it, its resistance at room temperature is 27 degrees centigrade is found to be 75.3. So when heating is small, current is negligible, heating is small. So that will be around at room temperature, that resistance is given. But when toaster is connected with 230 volt supply, then current will be very high. And then its average value will be 2.68 ampere. So there will be heating. So what is the steady state temperature of the nichrome element? The temperature coefficient of resistance of nichrome averaged over the temperature range involved is this. So this is the temperature coefficient. So let's calculate the value. Now R1 is given. T1 is question number 3. T1 is 27 degrees centigrade and R1 is 75.3 ohms. Current is small, so we are ignoring the heating it, so it is at room temperature. And at temperature, you have to find T2. The temperature coefficient of resistance is this over the involved. What is the steady state temperature of the nichrome element? So T2 you have to find. T2 we have to find. And at this temperature, resistance R2 is given by V by I. So this is 230 volt divided by 2.68 ampere. So I think this value is 85 point. This is 85.8 ohm. 85.8 ohm. So use this result. R2 is equal to R1 1 plus alpha T2 minus T1. So this will give you T2 minus T1 is R2 minus R1 by R1 into alpha. So this value is 85.8 ohms minus 75.3 divided by R1 is 75.3 and into alpha is 1.7 into 10 to power minus 4 per degree centigrade. 4. So if you calculate this value, T2 minus T1, this value will be 820 degrees centigrade. So T2 is T1 plus 820. T1 is given 27. So if you add this will be 847 degree centigrade. Clear? So this is the one example based on resistance dependence on the temperature. There is a linear dependence. Clear? Now solve question number 5. Let's solve question number 5. At room temperature, the resistance of an heating element is 100 ohm. What is the temperature of the element if the resistance is found to be? So again, you can easily find question number 5 also. But let's see question number 4. Question number 5 is similar, same type of question, so you can solve it. Now question number 4. The resistance of the platinum wire of a platinum resistance thermometer at the ice point is 5 ohm. Ice point means, let's say 0 degree centigrade. So R0 is 5 ohm. And steam point means 100 degree centigrade. So this will be 5.39 ohms. When the thermometer is inserted in hot bath, the resistance of the platinum is this. So let's see, that is at some temperature T. At some temperature T, or at some temperature T, this is 5.795, 5.795 ohms. Calculate the temperature of the bath. So now you will see R100 is R0 1 plus alpha 100 minus 0. So this will give you 100 minus R0 by R100 is equal to alpha into 100. This is equation 1. And then you have RT is equal to R0 1 plus alpha T minus 0. So this will give you RT minus R0 by R0 is equal to alpha times T. Equation 2. And let's see, divide 2 by 1. 2 by 1. So that will give you RT minus R0 by R100 minus R0. And this will be T by 100. So T you will get, RT is given as 5.795. R0 is 5 ohm. R100 is 5.39 minus 5 ohm into 100. So if you calculate this value, this is 345.65 degrees centigrade. Just check the calculation value. This will be the temperature. So this is the second type of question based on the temperature dependence of resistance. Chalo. Now let's see. Question number 7. For each concept, I am taking one particular question. Question number 7. Try to solve. So, question number 7. A negligibly small current is passed through a wire of length 15 meter. Length of the wire is 15 meter. Uniform cross-sectional area A will be 6 into 10 to power minus 7 meter square. And the resistance and its resistance R is 5 ohms. What is the resistivity of the material at the temperature of the experiment? At room temperature, what will be the resistivity rho? Simple question. R is equal to rho. R is equal to rho L by A. So rho is equal to RA by L. So let's calculate this value. So rho is given by 5 ohms, 6 into 10 to power minus 7, length is 15. This is 2 into 10 to power minus 7 ohm meter. 2 into 10 to power minus 7 ohm meter. So that will be the resistivity. Clear? Chalo. So one question is based on resistivity. Next is question number 8. A battery of EMF 10 volt is connected to a resistor. If the current in the circuit is 0.5 ampere, what is the resistance of the resistor? Simple question. Some resistance R is given. This is given as 3 ohms. And this will be 10 volt. Current I is 0.5 ampere. So I will be E by R plus R. So you have 0.5 ampere, 10 volt, R plus 3. So let's calculate the value of R. So this is 0.5 R, 1.5 is equal to 10 volt. So 0.5 R, 8.5. So R will be the 17 ohm. R will be the 17 ohm. What is the terminal voltage of the battery when the circuit is closed? So terminal voltage is simply I into R. So this is 0.5 into 17. So that will be 8.5 volt. This will be 8.5 volt. Clear? Chalo. Next question. Question number 9 and 10. You have to find equivalent resistance and then let's see. Question number 9 and 10. Try to solve 9 and 10. So question number 9, three resistances are combined in series. A part. Question number 9. What is the total resistance? So equivalent resistance will be 1 plus 2 plus 3, 6 ohm. If the combination is connected to an EMF of 12 volt negligible resistance, so obtain the potential. So what will be current in the circuit? Current is E by R equivalent. So 12 volt divided by 6 ohm. So this is 2 ampere. So what will be voltage drop across 1 ohm? V1 ohm is I into 1 ohm. So this is 2 volt. V2 ohm is I into, because in series current will be same. So this will be 4 volt. And V3 ohm is I into 3 ohm. So this is 6 volt. Clear? Now question number 10. Question number 10. It's a parallel combination. So what will be equivalent? 1 by 2 plus 1 by 4 plus 1 by 5. So this will be So this will be 19 by 20. So equivalent will be 20 by 19 ohms. If the combination is connected with a 20 volt EMF, negligible internally, determine the current through each resistor and the total current drawn from the battery. Current through each resistor. So first part is, A part is the equivalent resistance. In B, what will be current through 2 ohm resistor? Because voltage will be same. So voltage by 2 ohm. Voltage is 20 volt by 2 ohm. This is 10 ampere. What will be current through? Because in parallel voltages will be same. 20 volt by 4 ohm. So this is 5 ampere. And what is current through 5 ohm? 20 volt by 5 ohm. And this will be 4 ohm. So you know the meaning of series and parallel. And then you have this particular question, this you have to solve. So first you have to find equivalent resistance. These two are in parallel, then in series. Again, this is parallel. So make parallel combination of these two, then series. And then this is the internal resistance. You will get current. And then by using current division at these points, you will get current in each element. And then you should find the voltage drop. So this you have to find. Is it clear? So try to solve this question and other questions also. There are total, I think there is 21 questions. So you should try to solve these questions. First lecture, we have seen the basic problem. Now you have some more difficult problem is also there that you should solve. Is it clear? So we have to, in next lecture, we are going to complete this particular chapter. We will solve all other questions and then we will see the next chapter. Clear? Okay then. Meet you tomorrow, same time. Thank you. Thank you, everyone.